Подождите, там нет сложных пунктов. Сейчас, да. Да.
В общем, все остальные сразу, это не сразу. Ну вот, значит, решил наконец. Радостно отправляю, наверное, вообще не остановился, значит, проверку не делал. Отправить. И вдруг вижу, что у меня там галочка стоит. А я, оказывается, просто на автомате документ там листал и думал, ну просто очень непонятно, о чем думал, просто поставил типа там с мышкой поиграться. И забыл убрать.
Не там галочка стоит.
Да. Но я переотправил.
Ну ладно. Там, по-моему, по 3 попыткам, можете еще одну попытку, и будет 2/3. Ну, от этой, а все остальные как бы правильно сделайте. Там, по-моему, средняя по 3 попыткам считается. Ну, по 3 или по 2, сколько у вас будет, в смысле, по всем попыткам, которые есть, считается средней. Так, начинаем, да? Все, ну, я так понял, что все видели, да, тест этот в Smart LMS? Хорошо. Что? Дедлайн там поставлен, я вроде даже написал. Ну, во-первых, в Smart LMS должно быть видно какое-то 4 ноября или что-то такое. Я там месяц сдал, по-моему, на этот тест. Но это должно хватить, там вроде ничего сложного. Ладно. Нет, еще нет, но не запускайте, в смысле. Okay. We are still discussing general properties of the Fatou sets and the Julia sets, and whatever we have time to cover this today, we will say, and next time we will start a new topic anyway, namely local dynamics near fixed or periodic points. Speaking of general properties, what I also want to note is that, a theorem is that if you compute the Julia set or the Fatou set, it's just equivalent statements. If you take any iteration of your rational map, so let me say that I will always, so when I write f, I always mean f from CP1 to CP1 will always mean a rational function. A rational function of degree d. So I write d for the degree of this function, and if you take any iterate of this function, then the Julia set is the same for any k equal to 1, 2, and so on. So this is easy. It's an easy consequence of, well, this is of course equivalent to saying that the Fatou set will be the same. And the Fatou set is defined in terms of normal families. So in terms of compactness. If you have a sequence of iterates like that, so suppose that from any sequence of iterates of f, you can choose a convergent subsequence, then this is also true for iterates of f to the k, right? So in one inclusion is obvious. So in this direction, the inclusion is obvious. So in the other direction, the inclusion is more or less also obvious because if you have a sequence, well, suppose you given any sequence of iterates of this, of f to the k, you can choose a convergent subsequence. Now take any sequence here, sequence of iterates. So you consider f to the n1, f to the n2, and so on. By the way, I sometimes write the circle here, sometimes not. But anyways, I mean the iterate rather than the algebraic power. So if you have a sequence of iterates, then it splits into finitely many subsequences according to the residues of this powers mod k, right? And in each of the subsequences, you can choose a convergent subsequence because you have you are in the Fatou set of that, and therefore, well, they may converge to different. No, that's not a problem. You just fix some residue which happens infinitely often, and choose a convergent subsequence there, and that would be what we need, right? So this gives you inclusion this way. So the Fatou set and the Julia set do not change when you replace a rational function with any iterate of it. Now maybe a crucial fact about the Julia set is that eventually it covers almost everything, and now I can give a weak version of this statement and make it stronger later. So this is what Milner does. At this point in the book of Milner, there is a weaker statement, and then there is a stronger statement. So for a weaker statement, I would need a somewhat technical notion of an exceptional set. So first of all, let me give a definition. The grand orbit GO with index f of z, of a point z, is by definition the set of all points W such that there exists some m with f to the m of W. Well, there exists m and k such that some iterate of W equals some iterate of z. Yes? Большая. Нет, понимаете как? Ответ на этот вопрос очень простой. Чтобы понять, как это переводится, надо. У меня же есть русская версия этой книжки. Вот, более того, вот это так и переводится, потому что переводчик, который переводил это на русский язык, он был первым, кто на русском языке употреблял эти слова. Поэтому вот как он перевел, так это и называется по-русски. Вот, к сожалению, в русском языке не очень много, ну, на русском языке не очень много есть литературы на эту тему, поэтому здесь. Well, informally, what you take is, of course, you take all iterates of, so you play all iterates, you take the orbit of z. So you iterate forward, but you can also iterate backwards, meaning that for any point of the grand orbit, you can also take all preimages of these points, and they will also belong to the grand orbit. So the grand orbit is the minimal set stable under all forward images and all backward and all full preimages, and taking full preimages. So normally, usually, if you take any point, then this will be a lot. like because for any point you have many, or in general you have many preimages. So it's really a very exceptional, something very exceptional must happen to make this set finite. And let me say that Z is exceptional if the grand orbit of Z is finite. And then the exceptional set, E of F, is the set of all exceptional points. Okay, so the main the main thing to remember is that this set cannot be large, and generically this set is empty. If you choose an arbitrary, well, a generic rational function, this set will be empty. But there are some special cases which we need, well, to be careful. We need to describe the special cases, and let me say something about this exceptional set. So what we can say is that first of all, this exceptional set is no more than 2 points. So there are no more than 2 points in this exceptional set. Then we can also classify all cases where this exceptional set is non-empty. But let me also say that the second thing is that this exceptional set always lies in the Fatou set of F. And maybe the third point is that exceptional set is empty, or we can describe all other cases. Or maybe I can give a description right now. So if the exceptional set is non-empty, then either this is 1 point, or there are 2 points in the exceptional set. So if the exceptional set is just 1 point, you can map it to infinity. All points look the same, and you may always assume that the exceptional point is at infinity. Then F is a polynomial. And finally, if the exceptional set consists of 2 points, you can make them 0 and infinity. It's by a conformal automorphism of the sphere. You can map any couple of points to any other couple of points. So in particular, you can map any couple of points to 0 and infinity. Then F of Z is Z to the n for some n. Positive or negative, but it's Z to some power. Okay. This is what we can say about the exceptional set. And the proof is, of course, this is the main statement. So let me give a proof of this statement. First of all, suppose you have an exceptional point. So suppose that Z naught is an exceptional point, a point in the exceptional set. By definition, that means that the grand orbit of Z naught is finite, in particular the forward orbit is finite, so that this point is periodic. And you can write something like that. Z naught maps to Z1, it maps to Z2, and so on. And after finitely many steps, the point maps back to Z naught. Да. Что, константа? Нет, у константы нету никаких...
Нет, если z-венты умножить на константу.
А, z-венты умножить на константу? А, ну да. Да, хорошо, давайте умножим, да. Угу. Да, спасибо.
Все, z против всех точек. Одну функцию z в z.
У нас, да, вот это мы будем предполагать. Linear functions are not very interesting, and one usually exclude the case of linear functions because some general theorems can, well, also only hold for higher degrees. Okay. And I will use that. So I will use the assumption that d is bigger than 1 here. So suppose we have a picture like that. So we took any point, any exceptional point. Then we say that this point is necessarily periodic. So it has some period. The next thing is that every point in this cycle has other preimages, right? It has other preimages, and this, on the other hand, a picture like that is well, formally speaking, I should say periodic or pre-periodic. So a picture like that is not ruled out right away. But somehow I want to say that if a point has different preimages, then the ground orbit is going to be infinite. Why is that? So at some point, in order to... Ну, значит, вот чем это может заканчиваться? Это может заканчиваться только вот такой точкой, которая с кратностью d отображается в следующую, да? So the only way we stop is that we get an arrow of multiplicity d, and I hope it's clear what this means. Multiplicity d means that this point is critical, and that it has multiplicity d, that the derivative vanishes d times at this point. So this is the only, well, let me assume d is equal to 2 for simplicity, and let me try to draw some, to imagine some possibilities. So we may have a picture like that, a 3-cycle. Well, in principle, we may have another point like that, but then this point must be a critical. Then this point must be a critical value. Okay, and in general, for any vertex of this diagram, so you must have something. So either you have like a double arrow like that, or you have another arrow and a double arrow like that. Well, this is still impossible because here we have this point and another arrow here. Well, either you have another arrow, but you already used all critical points. So this tail will be infinite. Any point has two preimages now, okay? So we assume that d is equal to 2. That means that any point has two preimages counting multiplicities. On the other hand, we need to have a finite diagram, right? A finite diagram, so that every point is the target of two arrows. Every point is a target of two arrows. So this is an impossible thing for such a diagram, because for this point, there should be a second arrow. And since we already used all critical points, there are only two critical points for degree 2 map. This is also a crucial fact. There are only two critical points, and we already used all of them. Therefore, here we will get an infinite grand orbit, an infinite backward orbit. Да, но я более-менее сейчас...
Существовать конец такой цепочки. То есть почему мы не можем эту цепочку дальше развивать перед критической точкой?
Перед критической точкой?
Ну дальше тоже же такое. Это же вообще не может так.
Right. So that proves that any exceptional set, that proves that any exceptional set is periodic, right, immediately. So somehow I missed that thing, because indeed we can continue even here. We can continue taking further preimages, right? And this will also be a contradiction. So the only possibility is when we have a cycle in which both arrows are like that, right? Or perhaps we have two cycles like that. This is for degree 2. For degree 2, we have just two critical points. So there are only two double arrows for degree 2. And these are all possibilities for degree 2. Do you agree? Okay. So let's take degree 3. So for degree 3, in principle, how many critical points do we have? Да, well, in general, how many counting multiplicities? It will always be the same. It depends only on the degree, right? If you count multiplicities, then the number of critical points is what in terms of the degree? No? Well, f is equal to p over q, where p and q are polynomials. Okay, so you take the derivative. How you differentiate? F prime is equal to p prime q minus q prime p divided by q squared, right? And you equate it to 0. So this is, no, generically, if you rotate the sphere, then the degrees will be the same. So it's a very special case when one degree is different from the other. If the degree of the numerator is different from the degree of the denominator, you can easily fix that by rotating the sphere. That's not a problem. So in general, what you have to solve is this equation, and what is the degree of this equation? P and Q have degree D. 2D, но не совсем, потому что вы взяли производную. У этого степень d минус 1, у этого степень d. Да? Получается d минус 1 плюс d, 2d минус 1. Но на самом деле еще меньше, потому что старший член здесь сокращается. 2d минус 2. Вот это в общем случае верно. Well, this also follows from a general So this can be proved algebraically by solving this algebraic equation. You equate the derivative to 0 and figure out that this is an algebraic equation of degree 2d minus 2. Alternatively, you can use topology, and this is called the Riemann-Hurwitz formula. Do you know Riemann-Hurwitz formula? It's how you compute the Euler characteristic. Well, let me maybe a digression about. I will only give a very special case of this formula. So let me prove this topologically. So in terms of topology, let me compute. So you have the Riemann sphere covers. So a Riemann sphere covers the Riemann sphere with some branch points. So this is not a usual covering. This is not a covering in the usual sense, but this is a branch covering. Okay, so this is a branched covering, and you want to compute the Euler characteristic of the space upstairs, right? You know the Euler characteristic, but suppose you want to compute it. In general, if this were a usual covering, then the Euler characteristic gets multiplied by the degree, right? So if this were the usual covering, then the Euler characteristic of the total space will be d times the Euler characteristic of the base, right? But now I need a correction having to do with the existence of branch points. Since I have branch points, I need to correct it somehow, and точки ветвления, critical points. If you go downstairs, these are called critical points. If you go upstairs, these are called branch points, ветвления, or ramification points. Но какая здесь поправка? На самом деле, вот каждый раз, когда у нас имеется точка ветвления, да, это кратная точка, мы эту точку вот здесь просто посчитали лишнее число раз. То есть нужно просто вычесть все критические точки с учетом кратности. Вот и все, да? То есть мы должны вычесть вот это. So this is the correction, is the number of critical points counting multiplicity, because each time we have a critical point, this critical point is counted here twice, or more, twice or more times according to the multiplicity. Да. Кратность нуля, ну как, я считаю, что это одна критическая точка с кратностью 1. То есть как у критической точки, там кратность 1. Она не кратная, это простая критическая точка. У z в кубе уже кратность 2 у критической точки. Well, I'm sorry, this is a different question, but let me finish with this. So from this, it immediately follows that the number of critical points is, you know the Euler characteristic of the sphere, right? We know that it's equal to 2, so we write 2 is equal to 2d minus the number of critical points, and we conclude immediately that this formula holds. Is that clear? So this is called the Riemann-Hurwitz formula, and this is a special case. This is really a special case of the Riemann-Hurwitz formula. The general version of this formula deals with any branch covering, not necessarily of the sphere by the sphere, but any branch covering of one surface by another surface. Okay? Now, your question is about this. Да. Да, но это имеет топологический смысл. So the topological meaning of the multiplicity is that, a simple critical point is when two preimages of the same point merge together. Now, multiple critical point is when more than two preimages of the same point merge together. And the multiplicity of the critical point is this number of points merged together minus 1, just because I don't want to assign non-zero multiplicity to a non-critical point. Okay? Количество нулей в штрих. Почему? Именно так.
Ну вот если количество нулей в штрих, то штрих как рациональная функция имеет вот степень 2d, потому что знаменатель в квадрате. Тогда...
f' как рациональная функция. Мы не рассматриваем f' как рациональную функцию. Мы... Нет, мы не Нет, f' это не отображение сферы в сферу. Нет. Это важно. Это не отображение сферы в сферу. Когда мы приравниваем к нулю производную, мы как раз вот про бесконечность забываем в этот момент. Мы сначала поворачиваем сферу так, чтобы там не было, на бесконечность не было критической точки, а после этого считаем производную на комплексной плоскости, не в бесконечности. Вот, то есть это не инвариантное вычисление, и это существенно. Да. f' мы не рассматриваем как рациональную функцию, мы просто приравниваем к нулю. Yes, something will go wrong because when you try to figure out what happens at infinity, you first need to change coordinates. So it doesn't work with the same coordinate. Near infinity, you need to choose a different coordinate. Да.
Как научно можно так повернуть сферу, чтобы степени стали одинаковыми?
Достаточно, чтобы бесконечность не была критической точкой, чтобы бесконечность не была не критическая точка, а в результате.
Ну, например, for example, what is the meaning of the statement that the degree of the denominator is bigger than the degree of the numerator? The meaning of this statement is that infinity is mapped to 0. Just that. Okay. This can be easily avoided by rotating the sphere. And the same thing with the numerator. If the degree of the numerator is bigger than the degree of the denominator, that means that infinity maps to infinity. It's just a fixed point. Okay, you can rotate the sphere, and this fixed point will be somewhere else. So if you rotate the sphere slightly, then the degrees will be the same. Okay, so now let me continue with the proof of this theorem. We're describing the exceptional set, and basically in the degree 2 case, everything is done. In high degree case, there may be several cycles, but in each of the cycle, so in general, you may have a cycle like that, say a 3-point cycle or something, where each arrow has multiplicity d. Right? Now, what is wrong with that? So, or maybe, well, the period doesn't have to be 3, it may be more. A priori, it may be more, but we want to rule this out. Okay, now an arrow of multiplicity d means that the source of this arrow is a d minus 1-fold critical point. So this is a critical point of multiplicity d minus 1, right? And this point also gets multiplicity d minus 1. And this is the maximum we may have. We cannot have a third point of multiplicity d minus 1 because there are 2 d minus 2 critical points total, counting multiplicities. Therefore, we cannot have more than 1 2 cycle, or maybe 2 just fixed points. So the only possibilities are either like that, d, d, or like that, d and d. So in both cases, we have just 2 exceptional points and no more. Well, or just one, yeah, or just one, like that. D-стрелок. Вот если вы из этой диаграммы возьмете только одну часть, то вот это тоже допустимая вещь для такого. For the exceptional set. Okay. We proved the first part. So we proved that the exceptional set is just a 2-point set or a 1-point set. And the second part also follows because all points in the exceptional set we know by the proof of the first part. So all points in the exceptional set are critical. And periodic. Therefore, they are superattracting. In the sense that if you have, say, a fixed critical point, then a small neighborhood of this point is mapped to a much smaller neighborhood. It's like if you apply z squared or z cubed or whatever, a neighborhood whose radius is less than 1 becomes much, much smaller. Right? If you have a periodic point like that, you apply a certain iterate and you get attraction. So all nearby points get attracted to this point. That means that this point lies in the Fatou set because all iterates converge to this point, not just in terms of a subsequence, they just all converge to this point. So this is a Fatou point. And to prove the second part. Now the third part, suppose that the exceptional set is just the infinity. And that means that the diagram is like that the infinity is the multiple critical point of degree d. That is, the only preimage of infinity is infinity. Okay? Now let's consider a rational function whose only preimage of infinity is infinity. How do you speak of preimages of infinity in terms of classical complex analysis? Это называется полюсы, да, или плюса. So these are called poles. And saying that there are no preimages of infinity in the finite part of the plane means that there are no poles in the finite part of the plane. So you are dealing with a rational function with no poles in the finite part of the plane. And that means if there are no poles and the function is rational, that means that this is a polynomial, right? Because at infinity you also have a pole rather than essential singularity. And the classical theorem tells you that this is a polynomial. So then f is a polynomial. Now, the fourth statement is when the exceptional set consists of 2 points, 0 and infinity, and there are two cases here. So one case is the diagram like that. So 0 is fixed, infinity is fixed, and both have degree d. In this case, first of all, we know that the map is a polynomial because infinity is fixed with degree d. And we also know that, so we know that f is a polynomial. But we also know that 1 over f is a polynomial. Not 1 over f, but, well, okay. Let me say like that. F is a polynomial, and it has a critical point of multiplicity d. That means that f of z is divisible by z to the d times some other polynomial. And since the degree of f is d, then this other polynomial may only be a constant, right? So it's times a constant. And this case is done. Now the second case is when you have a 2-cycle with 2 arrows of degree d, and here you have 0, here you have infinity. Okay? So then the second iterate of f, will have this type. So it will have a constant. It will be a constant times z to the 2d. No. Rather d squared. Should it be d squared? D squared. Right? So the degrees get multiplied. Right? So it will be z to the d squared, and I want to say that f is just a constant times z to 2 minus d. This is what I want to deduce. So I want to say that f of z is maybe a different constant divided by z to the d. Well, maybe you don't even need that for proving. You just have a pole of multiplicity d. That means that you have a term like that. Well, plus maybe some other terms, but if you add something else, the degree will be bigger. Right? No, I mean, if you, well, any rational function can be represented as a sum of what is it called? Простые дроби into, well, I remembered that, how's it called? Well, anyway, the denominators are just powers of linear functions. So you can make all the denominators powers of linear functions, and you definitely have this because infinity has degree d as a critical value, and you cannot have anything else because anything else will make your degree bigger. Then the infinity will have some other preimages, and that's impossible. If you have anything else, then infinity will have some other preimages. Partial fraction expansion. I don't remember. Okay.
Можете, пожалуйста, повторить рассуждение, почему вообще стрелки кратности d здесь рисуем?
Почему мы рисуем стрелки кратности d? Окей. Давайте я вот здесь сотру и еще раз скажу. Пусть у нас есть цикл. Suppose we have a cycle, and suppose that some error of this cycle is less than default. Okay? That means since the degree is d, there must be some other arrow going to the same point. Okay? Now this point is non-periodic. Therefore, its backward orbit is infinite. You cannot have both points periodic, right, in the same cycle. Because, therefore, you cannot have convergent arrows, two different arrows with the same target. That's impossible, because one of the points will be non-periodic, and therefore it will have infinite backward orbit. Is it okay? Okay. So the theorem is proved, right? So this is this corresponds. This is also z to the n, but n may be negative here. Okay, we know that the exceptional set is very special, very exceptional indeed. And now let me also state the following theorem. Let's take a point in the Julia set and take a neighborhood of this point. So let U be a neighborhood of Z. Then I want to see which part of the sphere is covered by the images of this neighborhood. Namely, I take the union over all n's from n from 0 to infinity, the nth iterate of f, well, the nth image of u, okay? And I claim that this is equal to, well, it's maybe not equal, but it cannot be less than the complement of the exceptional set. So at most 2 points are missing here, right? And only exceptional points can be missing. This is a rather immediate consequence of Montel's theorem, because if you miss more than 2 points, if all iterates of the map restricted to the neighborhood U miss more than 2 points, that means you have a sequence of holomorphic maps to a hyperbolic Riemann surface, right? Because a sphere minus more than 2 points is a well, maybe even without hyperbolic Riemann surface. By Montel's theorem, this family is normal, right? Therefore, we get a contradiction with Z belonging to the Julia set, right? So if the iterates, all iterates restricted to U miss more than 2 points, then the sequence of iterates must be normal by Montel's theorem, and that's a contradiction. So the complement, yeah, let me write W for this set. And the first claim is that the complement of W is at most 2 points. So at most 2 points. On the other hand, the complement of W is backward and is on the other hand, this complement is what? Is backward invariant, right? I claim that all preimages lie here. Well, that's clear. If a preimage does not lie here, then it lies somewhere here. And therefore, the image cannot lie here. So it's just by definition. So if it's backward invariant, then it consists of ground orbits, entire ground orbits. But it's a finite set consisting of ground orbits. Therefore, this finite set must be contained in the exceptional set. Okay? So therefore, this finite set is a subset of the exceptional set. And that's it. Повторяю. У нас есть конечное множество, целиком состоящее из больших орбит. Потому что в нем не больше двух элементов. Потому что если бы было хотя бы 3, то все наши итерации на множестве U в эти 3 элемента не попадали бы. А если они не попадают в 3 точки, то они образуют нормальное семейство. Если они образуют нормальное семейство, то точка Z не может лежать во множестве жуля. Понятно? Вот. Это множество не больше, чем из 2 элементов, в частности, оно конечно. Но это, конечно, очень... это гораздо сильнее, но в частности, оно конечное. И поскольку оно состоит целиком из больших орбит, все его точки являются исключительными. Да. Все его точки являются исключительными. Но значит, это часть исключительного множества. Okay? So it's important that we did in this way. It's not enough just to note that this set consists of ground orbits, because we also need to know that this set is finite in order to conclude that this is a part of the exceptional set. Okay? Okay, now a stronger version of this statement is that you don't even have to take the union here. Is that you take just the neighborhood and some iterate restricted to this neighborhood maps it to all the sphere, but maybe an arbitrarily small neighborhood of the exceptional set. Well, at least it covers all the Julia set. That would be the statement. So it's enough to take just one large enough n, so that the nth image of U covers the entire Julia set. Maybe not the entire sphere, but at least the entire Julia set. And you can also say that the part of the sphere that it doesn't cover is an arbitrarily small neighborhood of the exceptional set. But we will prove it later. So for now, let me also give another characterization of the Julia set. Namely, I want to say that, well, maybe before I say something about characterizing the Julia set, I will, are there any questions? So let me do a digression. So I need some classification of periodic and fixed points. We will talk about this next time in more detail, but at least I need some terminology. So suppose you have a fixed point. F of z is equal to z. So this is called a fixed point. And if some iterate of z is equal to z, then this is periodic point. Where the smallest such p is called the period of z. So this is clear. Now, a classification of dynamical classification of fixed points or periodic points goes as follows. First of all, we can talk about fixed points because when we want to deal with periodic points, we simply replace f with the pth iterate of it. And then all notions introduced for fixed points will be applicable to periodic points as well. Now, if you have a fixed point, then the multiplier of z is defined as lambda is just the derivative. Well, of course you choose a coordinate chart in which z is not infinity. So you just choose in the usual sense, a coordinate chart near z, and in this coordinate chart you compute the derivative. And you may think that this derivative depends on the coordinate chart, but it doesn't, because this is the eigenvalue of the corresponding linear operator. The crucial fact is that the point is fixed. Therefore, the differential of the map is the linear map from the tangent space at this point to the same tangent space. And it has well-defined eigenvalue, just one eigenvalue because the space is one dimension, right? And this is well-defined, doesn't depend on the coordinate. It's just a number, okay? A well-defined number called the multiplier. Now, using this multiplier, you can classify the fixed point. For example, if the multiplier is less than 1 by its absolute value, so the modulus lambda is less than 1, then you say that z is attracting. And this has a natural explanation. Attracting means that you take the point z, take a small neighborhood of this point, that the small neighborhood is mapped strictly inside. Because if the neighborhood is small enough, then the linear approximation works well. I mean, all other terms are much smaller. And the linear approximation sends the neighborhood strictly inside. Therefore, the map itself also sends the neighborhood strictly inside. Moreover, if you take the sequence of iterates, then it converges to this point. So all nearby orbits converge to this fixed point. In this sense, it's attracting, okay? And it's called super attracting if lambda is 0. Question. Мультипликатор. Это вроде, да, это стандартно. Это не только в комплексной динамике вообще. Мультипликатор. Okay, so now there is some discrepancy in terminology here because some people say that super attracting is a special case of attracting, and some people think it's not. But that's not principal thing, so I will think that super attracting is a special case of attracting. Okay, now if lambda is equal to 1 precisely, then z is called neutral. Well, at least in the linear approximation, it's neither attracting nor repelling. But the dynamics at such a point, well, even the local dynamics, may be somewhat complicated, and there are two further subcases. So if z is neutral, then it may be that lambda is the root of unity, so lambda to some n is equal to 1 for some n. or not. Or, so in this case, Z is called parabolic. And if not, then Z is called irrationally neutral. Well, this case is further subdivided into Ziegel and Kramer, but we will not discuss it now. Finally, if the modulus of lambda is bigger than 1, then this is similar to the attraction case. But it's called the repellent case because nearby point get repelled from Z, get farther away from Z. So Z is repelling. Okay. So this is a basic classification of fixed points, and it also gives a similar classification carries over to periodic points. You can speak of attracting periodic cycles, super-attracting periodic cycles, parabolic cycles, and so on, repelling cycles. In order to define this, you just pass to the iterate, for which all points of the cycle become fixed points. Отталкивающее. Да. Есть русское слово репеллент. Да. Что? Не обязательно разбрызгивается. Может быть, намазывается, может еще, может просто там как-то просто пахнет, но главное, что это отталкивает, что это вот, что насекомые это не любят, и они как-то вот прочь летят. Хорошо. Well, what I want to say now is which points belong to the Fatou set and which point belong to the Julia set. So I claim that any attraction point belongs to the Fatou set. If Z is attraction, then Z is in the Fatou set. Do you understand why? It's for the same reason as we discussed for super-attraction case. Because the neighborhood gets smaller and smaller, and it converges to the point. So the entire neighborhood converges to a point, which means that the sequence of iterates converges just to a constant map. Right? If it converges to a constant map, then of course it's normal. Now, so this is clear. On the other hand, что, да. Да, мы сказали, что она не зависит от z, потому что можно ее инвариантным образом описать как собственное значение дифференциала. Дифференциал — это оператор из касательного пространства в себя, да, поскольку это пространство отображается в себя, у линейного оператора есть собственное значение, он не зависит от координаты. Да? Неважно, какую координату мы выберем, там все равно будет то же самое собственное значение. Okay, now if Z is a repelling, then Z is in the Julia set. Well, this is simply because if you take the nth iterate, and take the derivative of the nth iterate, it will be lambda to the n, and that converges to infinity. Therefore, no matter which subsequence you choose, the derivatives will also converge to infinity, and that's impossible for a convergent subsequence, right? So if a sequence of holomorphic functions converges, then their derivatives also converge. So this is a contradiction. And this is an important, so these are important things to remember, that attracting points are always in the Fatou set, and the repelling points are always in the Julia set, without any exceptions. Now, parabolic points are also in the Julia set, and that can be proved. Let me prove it somewhere else. Claim 3, if Z is parabolic, then Z is in the Julia set. Now, this is slightly more difficult than the second claim, but it's also, well, it's not that hard anyway. Let me just do one special case. So one special case is f of z is equal to z plus z squared, where the parabolic point is 0. So you will see how to do it in general from this special case. Okay? If you compute the nth iterate, then, well, you need to do some computation. But what you need to look at is just the coefficient with this z squared. And you can figure out that the coefficient with z squared will be n. Plus, of course, higher order terms. Do you agree with that? So the only important thing is that this n goes to infinity, and that will contradict normality. If you can choose a convergent subsequence, it's impossible that the second derivative goes to infinity, right? And this n is just the second derivative up to a factor of 2. Okay? So in all other cases, the computation is similar. Basically, if you multiply the root of unity, then take a suitable iterate so to make it 1. Now, the next term will be something times z to some power, and you can similarly argue that the corresponding coefficient will grow. Okay, now what the last thing I want to explain now, and that is rather important, is the following. So let me first define a Bayesian of attraction. So z naught and so on, z, say, m minus 1, is an attracting cycle. Let me write C capital for this cycle. Then the Bayesian Bayesian это как бы раковина, но по-русски почему-то говорят бассейн. Бассейн притяжения. The Bayesian of attraction of C is the set of all points W that converge to C under the iterates of the map. So you know that if you take any point nearby the cycle, so here you have the cycle. If you have small neighborhoods of all these points, then these small neighborhoods belong to the basin, right? Automatically, because you have linearization. And actually, this basin, so let me write B of C, well, maybe with index F. So this basin is an open set. Why it is an open set? Being in the basin means that after some number of iterates, you'll get very close to the cycle, right? Now, if you change the initial point slightly, then you still get to the same neighborhood. Well, maybe not to the same point, but you still get to the same neighborhood. But the entire neighborhood is in the basin, so the basin is an open set. Okay, it's open. And you know that, so by the claim we already proved, the entire basin is a part of the Fatou set. Right, because all the iterates converge to this periodic sequence. Okay? Then what I claim now, the theorem, is that the Julia set is the boundary of this basin. Note that there may be several basins, there may be several attracting cycles, and according to this, there may be several basins, but all of these basins have the same boundary, and this boundary coincides with the Julia set. Okay? So a basin may have many components, right? Usually, but not always. A basin is a union of disks, of topological disks. Now, the boundary of this union is not the same thing as the union of the boundaries. It contains the union of the boundaries, but there may be extra points, namely accumulation points of the entire components. Some components may become smaller and smaller and accumulate somewhere. And this is the theorem, so that whatever basin you take, if there is some basin, then the Julia set is the boundary of it. Now, there may be no attraction cycle, and then this statement doesn't have any sense. So the Julia set in general does not have to be a boundary of something. But if there is an attraction cycle, then the Julia set is the boundary of its basin. Okay. So this inclusion is obvious, right? Why? The basin itself is in the Fatou set. Now, what happens in the basin? We have some convergence in the basin, right? Outside of the basin, we don't have this convergence. Therefore, any boundary point cannot be a Fatou point, because near Fatou points, the iterates must do the same thing. The sequence must be normal, and if it converges somewhere on a part of a neighborhood, then it must converge everywhere. So any boundary point of the basin is in the Julia set. This proves this inclusion. Now, let me prove this inclusion. Let's take, I will use the theorem. So let's take a point in the Julia set. Take a neighborhood of this point, U. This will be a neighborhood. Then, by the theorem, or by which theorem, it's over there, I know that the images of the neighborhood cover everything except the exceptional set. In particular, they cover, well, some images will intersect the basin. Okay? But if, so, well, we know, well, an exceptional set is at most 2 points. And the neighborhood is infinitely many points. So they will intersect something else. So neighborhood, so f to the n of u for some n, so there is some n such that f to the n of u intersects the basin. Okay? Which means that u intersects the basin. Is it clear why? Because the basin is backward invariant by definition. If something lies in the basin, then all preimages also lie in the basin. Therefore, u also intersects the basin. Okay, and we see that any neighborhood of z intersects the basin, which means what? Which means that it's in the boundary, right? Well, it's not in the basin because it's in the Julia set. Therefore, it must be on the boundary. And every neighborhood intersects the basin. So it must be on the boundary. And we prove that for any basin, the boundary is the Julia set. For example, so an immediate consequence of this is a simpler definition of the Julia set for polynomials, because for polynomials, we have a God-given basin. Do you know which? There is one special attracting point for any polynomial. Exactly. So infinity is the super attracting point for any polynomial. Therefore, there is a basin of infinity, and the boundary of this basin is the same as the Julia set. So for polynomials, it's easier to define the Julia set. And for polynomials, let me state it as a corollary. If f is a polynomial, then the Julia set coincides with the boundary of the basin of infinity. So this is the boundary of the set of all points that escape to infinity. There is a set of all points that escape to infinity, and the boundary of the set is the Julia set. So sometimes this boundary, may look differently, and well, you've seen the pictures, some of the pictures at least. So sometimes the set of all points that do not escape to infinity is connected, and then this is the boundary of this connected set. Sometimes it's disconnected, like a Cantor set, then the Julia set is this Cantor set. But in any case, for polynomials, the Julia set cannot be the entire sphere, because well, there is the super attracting fixed point, and the Julia set is just the boundary of this basin. Any questions? Okay, then we'll do local theorem next time. Maybe you remember this English word. I'm not sure how to say it in English. If you have a rational function, then it can be represented as a sum of fractions, each of which has, well, over complex numbers. This is some constant in the numerator and the power of a linear function in the denominator. How is it called? Is it called partial fractions? I think it's something like partial fractions. So you know the notion, right? It's used when you compute the integral of a rational function, right? Is it called a partial fraction? Okay, never mind. I will look it up.